I'd like to invite, if I'm
Thank
not
you.
wrong, Felix.
Yeah, good afternoon, everyone. I will present you transpose, which is like transpose, but with a soft D. It was a free PyPy name. We all kind of know what we want to achieve at the beamline. And this is this experimental feedback loop. So we start a scan. The scan software normally triggers some detectors which produce pretty raw data. We want to analyze them and then either do a visualization for some scientists to make a decision on how to continue, or potentially, if the decision is easy enough, directly do that automatically and decide on how to advance the experiment. So most existing infrastructure at beamlines looks like this, that it's very siloed. So every detector basically lives in its own silo, has its own viewer, comes from its own vendor, and only at the very end, when the scan is done and everything is on file, it is possible to correlate together different acquisition methods. So the problem there is that the limitations are extreme regarding live viewing. So with a single data stream, you can already do quite a lot. So simple tools which are quite powerful, like azimuthal integration, live, you only need a detector image. You don't need any additional information, or the sum of a ROI or something. That works extremely well on a single stream. But beyond limits is, for example, a normalization to an I0, if that's required, or if you have like a motor position encoder measured during the scan to index the frames arriving by a big 2D detector according to this slow data rate. So we need a lot of additional sources in addition to the standard detectors, like big 2D ones, which are, for example, motor encoder values, or a XRF spectrogram, or a simple small camera in addition, or even then we want metadata from the control system itself. So we also want to bring these in. And basically, we want an event formation engine. This is nothing new, like a lot of other facilities do similar things. So we have a hardware trigger source, which triggers detectors in an arbitrary fashion. And then we form an event and analyze on an event basis and not on a per stream basis. On the right here, you see an example of how such a trigger map might look like. The two detectors on the left, the two columns, produce a frame on every trigger, but we might have slower devices which could not keep up with the high trigger rate, and therefore we have non-uniform triggers, and we need to accommodate the event formation for that. One example is also if we have super large 2D detectors, they might have a stream per module or per module group, so already assembling a full image of a detector is not easy to do if you only have access to one stream. So there is one big problem, which is this bottleneck. If we bring together all the data sources, then the bandwidth explodes tremendously. But in this community, at least, there is one solution which is also has a red logo and solves all your distributed problems. And this is Redis. It helps a lot to distribute a system from a single point of failure into a well-orchestrated microservice architecture. So because like the tools, it's basically gluing together tools, we looked around what else exists, because we should not reinvent the wheel just because we want to learn something. There are amazing distributed stream processing tools, for example, Apache Flink. This has the exactly once guarantee, so it caches events and makes sure that they are processed. If you want to cache events at like multiple gigabytes per second, you extremely fastly run out of memory. But it works extremely well for small events. We unfortunately don't have small events. There is Hummingbird, which I just recently learned of, is Pulse from Pulse Facilities. I think it started at Slack. I've seen it at EUXFEL. But it's very tailored to pulsed facilities, which did unfortunately not work for us. DESI has Onda and Hydra. I'm not sure if they're no longer maintained. Probably the audience knows more. I found a lot of broken links in the documentation and was unaware of where the project went. And then, of course, Evox, we heard of it. It works extremely well. It has a large ecosystem, and it can ingress data from Bliss. And the missing point we had is that we need like a system which easily does like 10, 15 gigabytes per second in processing, which needs to be distributed. So parallelization is the solution. So we do a map reduce. Every stream goes through an event formation unit, which spreads it to a lot of workers, and the workers have a map function, which maps the big data stream into hopefully smaller ones. There is a cool feature in this load balancing, which is constraints. So we can say if we want the difference in time, we can say that 2n and 2n plus 1 event goes to the same worker, and then we can have local states in the worker. Or we can send stuff to debug, but we're still missing like long-running inter-event analysis. And therefore, of course, the reduce step is useful. You can do something at line speed. This is appending to a list, summing small values which fall out of the map. And normally in the reduce step, we also take care of visualization. So there, we send, like as a visualization interface, we send data to an HSDS server, which behaves like an H5 file, but you don't have all the swimmer problems because the web service providing the HSDS basically takes the lock on the file. And then whatever viewer you want can access that. So we have dedicated live viewers as applications. You could use H5 Web, as you heard yesterday, or Silks. We just landed a commit in main, and hopefully in the next release, you can just point it to an HSDS server and view the data live from there. Behind the scenes, it's basically a big mesh of ZMQ streams. All of them are native Python. If you want more performance, there are a few components in Rust. Like as long as your language has bindings for ZMQ and Redis, you can replace one of the components. We have scientists who are not comfortable writing analyses in Python, so they could build a C++ worker for the map function. And of course, like yesterday, someone mentioned that you should build very robust infrastructure and then put very fragile code on top. The infrastructure is very heavily tested. The whole thing has end-to-end PyTests, including also the Rust components, and it's strictly typed, so all the messages are validated using Pydantic. The performance are something interesting I haven't seen for the other frameworks. In the small event regime on the left, like a few kilobytes per event, we are basically limited by the event loop of Python, which is about at 12 kilohertz or something of events. And if we go bigger with the frames we process, like at 2 megabytes or something, we are limited by the bandwidth ingest of a single TCP stream. The cool thing is here, you see on top, we have like parallelized ingests. A single ingester processes about 3 gigabytes per second, but if we have 8 of them, we nearly increase it by a factor of 8 to around 16 gigabytes per second. This runs on a cluster with 100 gigabit links, so we're at least saturating 2 network interfaces with 2 machines fully. And we don't see that this slows down. The end-to-end latency is about 2 milliseconds through the whole pipeline from detector image until the reducer. To actually help scientists develop live analysis, because it's super hard to do that. In a Jupyter notebook, you can always go back once, but if you have a live stream, you cannot really go back. So we provide a recording function which records an experiment and just dumps all the streams, and then you can locally download these onto a laptop and replay often locally on your laptop to develop the live analysis, and then you bring it to the Beamline, we deploy it, and you get the views you want. A few case studies. At Nanomax, we do XRF mapping. So the worker function is a PyMCA fitting, which also takes the positions from the motors of our scan software and the XRF spectrum from our Express 3. At Nanomax, we do beam alignment with center of gravity from a small Basler camera. We provide, for example, a pileup file, which is something super simple and now was implemented by the Beamline themselves. So they just accumulate in every worker and at the very end dump them to a file and have like a pileup file for every scan. Or for live tomography, we merge together the like 16 megabyte frames of our huge Orca camera together with the encoder position from a Panda box where the motor are. So we know, like, we can augment the high data rate stream with motor angles to then feed into the reconstruction engine and exactly reconstruct them from the slice where it's possible. It's on PyPy. You can just install it directly in whatever environment you want and start using it. You don't need anything. If you want to deploy it, it's Docker Compose. We have a Kubernetes cluster. We deploy it with Helm. There is documentation available on Transpose. And if you want to work on that, Max 4 is hiring. Please come or talk to me or email to Paul. Great opportunities. Thanks a lot.
Okay, well, a short question.
Thank you, very interesting. If I understand correctly, because I'm just introduced to Transpose right now, is that the workflow that's doing the data analysis and the streaming, it's interconnected. Let's say you can't do, let's say, a Transpose workflow on something that is not streamed, right? Exactly. So it's the same thing. It's interconnected.
It mostly works for streams. So the input is a stream. You can recreate the input from an H5 file if you want to, but then a stream normally contains more information, like there are sequence numbers and stuff, which are never end up in the H5 file. So you need to recreate this data if you want to read it from an H5 file. And it's specifically not targeted at offline analysis.
Okay. Yes. Yeah. Thank you.
Yeah.
Okay, so time is ticking by 5 minutes, so I have to say thanks.